All attendees are in listen-only mode.
Hello, everyone. We're going to wait for a few minutes until everyone is able to join, and I will make a start. I can see a few people still joining. I'm going to wait for a couple of minutes, and then we can start. Okay, I think I will make a start. Hello, everyone, and thank you very much for joining us today to this webinar. I'm particularly excited about this webinar, and the topic I think is of special relevance, at least in UK right now, to the big importance of the high-speed 2 scheme. The aim of today is to talk about one particular problem for high-speed bridges, that's resonance and dynamic amplification, and how we can assess the dynamic behavior of the bridge using MIDAS. So the webinar, it's going to be structured like this. First, I will just make a quick introduction about myself, my company ARCADIS, and about the project of HS2. Then I'm going to make an introduction on the problem that we are going to talk about, this resonance and dynamic amplification, how this has been addressed in the Eurocodes. Then I'm going to talk a little bit about two key factors to consider, that's stiffness and mass, the eigenvalue analysis and how to use it for this particular case. Then I'm going to jump to the how to set up a time history analysis, the result interpretation from the results we get from this time history analysis, and finally I will make a conclusion. So my plan is I'm going to go with the webinar. If you have any questions, you can submit it at any time, but then I will aim to respond them at the end of the webinar. Okay, so very quick introductions about myself. I'm Pedro Faras. I'm a principal bridge engineer in ARCADIS, UK. I'm based in London. I have more than 10 years of experience designing bridges and civil structures. I have an extensive experience in the use of finite element methods in structures. I've been involved many times in advanced analysis and complex structures, and I've been combining that with lecturing finite element methods in the civil engineering faculty in Barcelona for 5 years as well. I've included here a few projects that have been involved, like the diagonal motorway in Spain, the high-speed line feasibility study in Poland, in Saudi Arabia. I work with the Abu Bakr motorway and Jeddah Metro, and probably the two biggest schemes being developed in UK right now. That's the Lower Thames Crossing and obviously high-speed 2. About ARCADIS, ARCADIS is a global company with services that range from design to consultancy, from natural assets to built assets. Proud to say that it has been chosen as Company of the Year by the New Civil Engineer Awards. We have more than 27,000 people around the world. We have over 300 offices, and we are active in more than 7 countries. Just to give some facts and figures, our full year gross revenue was 3.2 billion euros last year. And in terms of bridges, ARCADIS has a very long history and a lot of expertise in bridges. Our team here in UK is around 100 people. We are more than 350 around the world. And we have been involved in bridges like the Milo Viaduct. Couldn't resist to also portray the Tower Bridge that was designed by a former company of ARCADIS many years ago. Refurbishment of the Albert Bridge in London as well, the Rotherhithe Bridge here as well, the Teruel Bridge, or the Vasco da Gama Bridge. Yeah. We have a big team, a lot of expertise, and we love the technical challenges. About high-speed 2, probably you are already familiar with it, but just a very quick introduction. High-speed 2 is because high-speed 1 in UK is the line that is currently in service connecting the Eurotunnel and London. So high-speed 2 is the project that is being developed at the moment to connect London to Birmingham, Midlands, and then Manchester and Leeds. ARCADIS is the lead designer with working in joint venture with Zetek and COE for the packages C2 and C3 of the phase 1. Phase 1 is the first stretch that goes from London to Birmingham, and packages C2 and C3, they are the central packages, and it consists on the line crossing mainland, and it has above 80 kilometers of railway line, 86 bridges, 14 viaducts, and many other major civil structures. Now that I have introduced the scheme, I'm going to introduce the problem. So what's this problem of resonance and dynamic magnification? Well, the classic approach of designing bridges is to use static analysis, where you analyze forces, deflections in your bridge under certain loading, and if it's a bridge, a rail bridge, then you will use maybe a moving load to check different positions on the train. But it's just a series of static analysis that you are checking. You extract an envelope and then you multiply by a factor, a dynamic amplification factor, to take into consideration the dynamic effects. And this classic approach was the one that was used on the first French high-speed line between Paris and Lyon. And when this line was put in service back in the 80s, some problems were observed in the line, in some of the bridges. So some bridges exhibit some resonance phenomena, and the ones that did, it was observed that the ballast degraded very, very quickly. There was a rapid track deterioration, and also that short span structures were the ones with more severe effects. In view of that, in a joint effort in Europe, a committee was constituted to study this problem. And after running a series of studies and tests, they concluded that this problem is especially relevant for speeds, train speeds over 200 kilometers per hour, and for speeds over this value, there is a high likelihood that you will have resonance effects. And if that happens, using this classical approach of doing a static analysis and then multiplying by a dynamic amplification factor, that's unable to predict the resonance effects. And the other thing is that you need, for these kind of bridges, you need to check the deck acceleration. The committee as well established a series of rules and guidance for doing the dynamic assessment of bridges, and these rules now have been implemented in the Eurocode. So what you see in the Eurocode is basically the conclusion of this committee on this particular problem. What is the difference between when you have a line that is on ballasted track or a line that is on ballastless track? Well, these problems of resonance and deterioration manifestate in different ways. If you have ballast, when the accelerations in your deck exceeds 0.7 g, the acceleration of gravity, then the grains in the ballast lose the interlock between the grains, and they're not able to withstand horizontal and vertical forces anymore. If they don't withstand these forces, they are not able to keep the sleepers and tracks on place, and that leads to have problems with the track alignment, and then quick deterioration and the risk of derailment. But if you're using ballastless tracks, you don't have this problem with the ballast, obviously. But when the acceleration exceeds the gravity acceleration, then the contact between the wheel and the rail is lost. And that also leads to a very quick deterioration of the track and as well to the risk of the derailment. The committee also concluded that there is a big difference between single-span structures and continuous structures. And continuous structures are able to reduce these resonance effects, but the single-span structures are the ones that are severely affected. And they introduced as well the concept of resonance speed, and the resonance speed is the speed of the train that makes your bridge to go to resonance. And this speed doesn't necessarily have to be the high speed that your train can run over your bridge. Can be any speed between, let's say, 200 kilometers per hour and the design speed of the line. Now, how all this has been established on the Eurocodes. I'm going to do a very quick review on the provisions in the codes. So the first thing is about the dynamic amplification factor. And the codes differentiate two different scenarios. One, when a dynamic analysis is not required, and another scenario when a dynamic analysis is required. If it's not required, you can go with the classical approach. You check your structure with moving loads, static moving loads, with load model 71, model SW0. If appropriate, you can use SW2. And then the results from this static analysis you multiply by dynamic amplification factor. That is a value that you can derive basically with parameters of track irregularities and a determinant length that depends on the element that you are checking. If you're checking the main girders, it will have a determinant length. If you're checking some cross members, it will have another determinant length. And with that, you're able to design your bridge without having to do any dynamic analysis. But in some other cases, you do need to do a dynamic analysis. And if that's the case, you still have to do your static analysis and apply this dynamic amplification factor. But additionally, you have to run another analysis, and this is the dynamic analysis with different load models, the HSLM, the high-speed load models, and the real train, the train that you're expecting to run over your tracks. That's a real train. And then you have to multiply it by first a value that is the amplification of forces and deflections due to the dynamic behavior of your bridge. This is the this first term over here. And you have to multiply it by the maximum dynamic response. So you have to run a series of trains and a series of at a series of speeds, and you have to take the most onerous one and multiply the static results of these trains by this factor. And as well, you have to include an additional parameter for track defects and vehicle imperfections in the equation. So we have these two scenarios when is required and when it's not required, the dynamic analysis, but you might question now, how do I know if I need dynamic analysis? Well, the codes give you a nice flowchart like this one. I'm just, for the sake of brevity, I'm adding here just one flowchart from the UK annex, and that's the one for simple structures. Simple structures is the ones that behave like a beam element between supports. And there is another similar flowchart that is for complex structures, that are the ones that do not behave as a beam between supports, but they, for instance, have grillage or orthotropic behavior or cable state or any more complex structures. You have to use a different flowchart. But this flowchart gives you some criteria to define if you will need or not a dynamic analysis. Later on this webinar, I will introduce a case study, and for this particular case, I'm going to show you how to use this flowchart and determine if you need or not this dynamic analysis. Right. The accelerations check. We have said that if we need the dynamic analysis, we have to check the maximum values for the dynamic results, but we have to check acceleration as well. And which are the limiting values that the code imposes? Well, the code recommends a couple of values, different values if you're with a ballasted track or a ballastless track. If your track is on ballast, the maximum acceleration that you can allow in your deck is 3.5 meters per square second. And that's to make sure that you don't have any problems with the stability of your ballast. That's basically the 0.7 G that we have seen previously with a factor of 2. If it's a ballastless track, then you should use a maximum acceleration of 5 meters per square second. And in this case, is to ensure that the contact force between the wheel and the rail doesn't reduce beyond acceptable limits. But these two values are recommendations from the Eurocode, and the UK annex from the Eurocode tells you that these values should be determined per specific project. And another thing I think is worth mentioning is what we are talking here about is this amplification problem and the problems with safety and track deterioration if accelerations go beyond some limits. We're not talking about passenger comfort criteria. Passenger comfort is covered somewhere else in the code. Okay, let's jump now to main parameters for our analysis. That's stiffness and mass. As you probably know, but these parameters are key for any dynamic analysis that you're going to perform. And in this case, bridge stiffness, you should consider this value very carefully, because if you overestimate the bridge stiffness, then you overestimate the fundamental frequencies of your bridge, and you will overestimate as well these resonance speeds, and you may miss resonance phenomena. You might be underestimating the forces on your bridge, and that's put a risk in the safety of your bridge. So it's very important that you use a lower bound estimate of the stiffness. Things like shear deformation, you have to make sure that you're considering shear deformation if you're using beam elements. And if you're using concrete structures that you allow them to crack by design, like a composite structure that you expect the top slab to crack near the supports, you need to model the crack properties in your dynamic model. You cannot use cross properties, because then you will underestimate the resonance effects. When we are talking about mass, then gets a little bit more complex because you need to consider lower bound and upper bound of mass. The lower bound will help you to estimate the maximum accelerations in your bridge, and then when you're using the upper bound, that's gonna help you to define the lowest speeds that you can get resonance in your bridge. So you have to run two different scenarios with two different masses to make sure that you're covering every possible situation. For instance, in this upper and lower bound, when you have a ballasted track, you have to consider two scenarios for the ballast. One scenario is when you're thickness of ballast is the minimum allowable in your bridge, and the ballast is dry and the ballast is clean, so it has a lower density. And the other scenario is when you have an extra thickness in your ballast to allow for track lifts. So thickness is greater, and then you have to consider dirty ballast and with a saturated density. And these two different values is going to give you the two different bounds for your mass. You also have to make sure that you're considering masses for everything that goes on top of your bridge, and that's the rails, sleepers, parapets, overhead electrification, everything that will contribute to the dynamic behavior of your bridge. Okay, so after this basic introduction, let me introduce this case study. This is a case, very simple one that I think it's useful for understanding the basics of how to run this dynamic analysis. It's basically a 30 meters bridge, single span concrete box with the dimensions that I'm showing right now. So if we want to first check if we need a dynamic analysis and then analyze this dynamic behavior, the first thing that we have to do is go to this flowchart. And you start by checking the speeds. In this case, we are assuming that that's a bridge on a high-speed line that with speeds up to 400 kilometers per hour. So we have to go down. We said that is a 30-meter single-span bridge, so that's down again. And the next check that we have to do is that we need to check if the fundamental frequency is within limits of the figure of the national NH14. That's the figure that I just introduced here in the right-hand side. So we need to assess these fundamental modes and fundamental frequencies to see if we are within limits or not. So to do that, I've prepared a model like this one, a very simple one. Is basically a beam element representing this concrete box, 30-meter span, and I've subdivided the beam element with nodes every half a meter. My boundary conditions are simple supported in both sides. It's rotationally fixed because I'm assuming that you have we have a couple of bearings at each supports, and the axial load is fixed on one of the ends. Just to show more or less how that looks like, that's this section, and that's a 30-meter single supported span. I've defined the section properties using this menu in MIDAS, where you can define the sizes for a concrete box. And it's very important that you make sure that you tick this box to consider shear deformation, to make sure that you're not overestimating the stiffness of your bridge. I've also defined the material, C45, with all the parameters from the codes. And then I've included first all the loads that I have on top of the bridge: ballast, sleepers, drag, parapet, everything else. I've represented that as a load. But since I have to run an eigenvalue analysis, I converted that to a mass by using loads to masses. So I'm converting every kind of load that I have. In this case, it's just a beam load, and all the directions are important and a factor of 1. So I have these loads for my eigenvalue analysis will be considered as a mass. The other thing I have to make sure is that I'm considering the mass of my concrete box. And to do that, you have this menu in structure and structure type, and you have to make sure that you're ticking to convert the self-weight into masses, and that's to be used in 3 directions. With that, I have a model that has the stiffness properties, and I have boundary conditions, and I have the mass properties. So you should be ready to run a dynamic analysis. Eigenvalue analysis to get the fundamental modes. If you do that, in results, mode shades, preparatory mode shades, you can just check which are your results. For instance, for the first mode, you'll have something like that. That's vertical bending. I'm gonna just change it a little bit. So something like that. Mode number 2. That's horizontal bending. That's the view from the top of the bridge, and you can see how this mode makes the bridge bend laterally. Mode number 3. Oh, what happened here? Well, if you're checking these results, you will see that MIDAS is not showing any displacement. But the truth is, no, you cannot see that on this window, but I'm going to show that here in the presentation. The third mode, that's this mode over here. This has a mass participation factor of 80% in rotation in X direction, and that's torsion. So this you have to be very careful to identify these kind of modes, so you don't think that is a mode that is not relevant, but this actually is very relevant. It's the first torsional mode of the structure, mode number 3. Okay, and you continue extracting all the results until you get a table like this one. You may wonder, how many modes do I need for my analysis? Well, the Eurocode give you some recommendations, and it's telling you that you have to extract as many modes as up to 30 Hertz, or 1.5 times the frequency of the first fundamental mode of the member that you are designing. If it's a main girder, so the vibration of this member. But if it's a cross member, or if it's a cantilever or another secondary member, you have to consider the fundamental frequency for this specific member, or at least 3 vibration modes for the member that you're designing. In this case, we are just we have this main member that is acting as a beam because it's a very simple structure, this concrete box. So I've run up to 30 Hertz, so I extract up to 5 different modes. And if I use these results in my flowchart, this was when we end up before in this check here, and we needed to check if the fundamental mode was within the limits of the figure 14, and we have a bridge of 30 meters. That's this value over here. The first fundamental frequency was 6 Hertz. That's its value here. So we see that we are within limits. So fine, we can go down and continue in the flowchart. Next check is to check if the torsional, the first torsional frequency is greater than 1.2, the first bending fundamental frequency. And if we go back to our results, we see that the first bending frequency was 6. The first torsional was 20, much greater than 1.2 times the bending one. So that's a yes. We can continue. Right, is skew less than 15 in this case? Skew is 0. So we continue. And the code is telling you that you may use only the bending mode for your dynamic analysis, but definitely a dynamic analysis is required for this kind of structure. these recommendations saying that you may use only the bending modes, you will see later on that I will use bending and torsional modes, because for me it's almost as easy to use all the modes I have already extracted, that just picking the ones that are bending. So that's why it just says may not use, you must use, it says that it's optional to use only the bending modes. Right, so conclusion. We need to run a dynamic analysis. So how we do that? Well, first, which kind of time history analysis we need to run? It's a linear or is a non-linear analysis? Well, usually the structures that you will be designing, you will expect the structure to behave on the linear range when you're applying the live load. So you should suspect that you will analyze the structure for within the linear range. It's not explicitly said in the codes, but the assumption is that you will use a model integration method because that allows you to pick the modes that are relevant, as I just seen on this flowchart. And the other thing, that's a transient problem. It's not a periodic problem, because obviously you have the train runs over your bridge and then goes away, and there is no load on top of your train. Right. So these are the main characteristics of your time history analysis. What else? Timestep. Which timestep we should use? Well, for the timestep, there is no any recommendation in the codes, in the Eurocodes, but the report that this committee prepared, that I've already introduced before, gives a series of recommendations of which is the maximum timestep that you should use. And you should use the minimum timestep of these 4 values. These formulas depends on the frequencies that you have extracted from your eigenvalue analysis, the span of your bridge, the fundamental frequency, and well, the last of them all is that you shouldn't use a timestep that is over 1 millisecond. Why is that important? Well, it is important. I've just added a figure here. In this figure, I'm just trying to describe a response of a structure, and I've run 2 different analyses. One with a timestep of 5 milliseconds. That's the blue line, and you can see that is describing quite well how this structure oscillates and has a peak value of around 1. And then I have the same problem, but I have chosen to use a timestep of 40 milliseconds instead, and that's the red line. If I do that, you will see that then the amplitude of the oscillation I'm extracting from this result is reduced significantly. Actually, that's around half of the amplitude of the first analysis. So I'm underestimating the peak values by half, and that's why it's very important to choose the appropriate timestep. Another parameter that we need to know to set up this time history analysis is damping, and the Eurocode gives you some recommendations. And the damping values depends on the span of your bridge, and depends on if it's steel, if it's composite, pre-stressed concrete, if it's reinforced concrete. And the last thing is the loads that we should use. Then the Eurocodes introduce you on different loads. The first set of loads is for doing this acceleration check and extracting the dynamic amplification factor. And there are different load models. The first load model is HSLM-A. That is a set of 10 different variations of load model, like the one that is on the figure here. And basically, it's a series of coaches with axle loads, and the variations is because you can change the values of axle spacing, the length of your coach, and the number of coaches that you're going to use. The purpose of having these 10 variations is to cover all possible situations, all possible trains running over your bridge. For simple structures and spans less than 7 meters, you have another load model, that's SLMB, and the other load model that you have to run is the real train. As I said, this is for the acceleration check and for getting this dynamic amplification factor. But another thing that you have to do is a fatigue check. And for that, the codes give you different load models, 12 different trains that you have to run on top of your bridge, and how you have to mix these trains and how frequently they run over your bridge. And all these different load models, you have to run them over your bridge at different speeds, trying to catch up these resonance speeds. And speeds, according to the code, have to go from 40 meters per second, that's roughly 140 kilometers per hour, up to 1.2 times the maximum line speed. In high speed 2, we are considering a maximum line speed of 400 kilometers per hour. So that means that we need to run this time history analysis for speeds up to 480 kilometers per hour. Right, so we have these train models, and the question now is how we can introduce these train models to the dynamic analysis. Well, these load models will be basically axles moving from on top of your bridge. And here I have an example of one axle load. This is this load over here that is on top of one of the nodes on your bridge, assuming that you have modeled that as a beam element, but it's the same thing for any other element. And that this load starts moving when the time is goes most forward to the next node until it gets just on top of the next node. Then we don't have a way of introducing loads as such as that. Well, we can transform these moving loads to loads in nodes that are increasing and decreasing depending on the position of the axle. So if the axle is on the first node, we'll have 100% of the axle force on the first node. If the axle is between the two nodes, then we will use just half of the axle force in the first node and half of the axle load in the next node. And until the axle moves to the next node, and then the first node will have 0 force, and the next node will have the full axle force. And this is represented as these time functions. So it's a time function that is value of f when the time is equal to j, and when time starts to increment, is going down until the axle is on top of the next node, and then this is 0. This is for the first node I, and for the next node I plus 1. It's a very similar function, but it starts with 0 and it starts increasing until the axle is just on top of this node, and then you have for 100% of the force applied. So this way allows you to transform what is a moving load to dynamic nodal loads. Okay, that's for one axle. What happens when you have a series of axles? That's your load models from the Eurocode. Well, if we are trying to get a time function for this first node for a full train, then we run the train on top of your bridge, and every time that axle just steps over your node, you will have one of these peaks here. That stands for the first node. What happens if you want to extract the time function for another node? Well, the time function is exactly the same. but with a delay compared with the first time function. This delay is just the time that takes the train to get from the first node in the bridge to the blue node. Okay, so with all this, you have all the information you need to set up a time history analysis. So what I'm going to do is go back to my model, and I'm going to start setting up this time history load case. So first thing, in loads, dynamic loads, and load cases, you're going to set up your time history load case. So I'm going to call it test. I'm going to run this test train at 300 kilometers per hour. As we said, this is a linear case, model integration, and it's a transient problem. The time increment is 1 millisecond, and the damping ratio, if you check the code for a pre-stressed concrete structure, is 1%. Right. With this, you have set your load case. Next thing is to set up, to describe the time function. And then we go to load again, and time history functions, and add time function. And then I'm going to create a time function under the same name, test train at 300 kilometers per hour. I want to be that a time function that describes a force. And then we want to use this graph that we have just shown in the presentation. I want to introduce that to my model. So how we can do that? Well, what I've done is I've prepared an Excel spreadsheet that takes every load model and transforms it to a time history function using the train speed, using the spacing between nodes, and obviously the train model. So if you change here, I want to use, for instance, HSLM A5. This time function for the whole train is going to change. If you want to use another speed, then everything will be updated for this different speed, or also the spacing between nodes. If you want to use another spacing, then that will change the time that takes the train to go from one node to the other. For this case, to make it brief, I'm going to use a test model. My spacing was 0.5 meter, and I was aiming to have 300 kilometers per hour train speed. So I have this kind of time function, the one that is plotted here, and the values are just in this table here. So what I'm going to do is just copy these values in my MIDAS model. I'm going to first prepare the rows, so just inserting arbitrary values, so I can just then copy and paste. Right, so you can see here that you have the time function that we had on the Excel spreadsheet as well. So we have the time function. Fine, we have the time history load case, we have the time functions. What else? Well, next thing to do is the dynamic nodal loads. How are they described in MIDAS? Well, first, they're assigned to a specific load case. This is the test at 300 kilometers per hour. Fine, this is the one that we want to run. Then they are assigned to a specific time function, and this is the one that we just described, and that's time function for a force, so fine. And this force is going to be in Z direction. And it's going to be with a factor of -1 because it's going to point downwards. Right. and which node we should apply? We have this this factor, and there is another factor, another value that we have to insert. That's the arrival time, and the arrival time is the time that happens between your start your analysis and when your time function starts applying to your node, and that's this delay that we have introduced before. This delay between the first node and the node that you're considering. So to do that, what I'm going to do first is just select all my nodes and assign them this dynamic nodal load case with an arrival time of 0. And then I will update that in a tabular format because it's just easier for me. If you go to tables and you go to static loads and dynamic nodal loads, you have all this information in a tabular data. And in my spreadsheet, I have this arrival time as well. So I'm going to use that. So I can just copy my arrival time into my MIDAS model. Like that. Okay. So for the first node, arrival time obviously is 0 because the train starts here when the analysis starts. Second node, well, you cannot see it for because there is only 2 digits, but takes 6 milliseconds to reach the second node, 12 milliseconds to reach the third node, etc. Right? So we have everything in your model. Now you can just close, and if all your inputs are right, you can just run the analysis and you will get the results. Okay. I'm going to jump back to the presentation now and go into the next section. That's results interpretation. That's very important for a couple of reasons. The first is that you want to make sure that your analysis is right. And secondly, because you need to be careful when extracting the results, so you're getting the peak values for forces, deflections, and accelerations. For instance, for this case study, the model that we are performing, we can extract values as envelopes. I'm going to show that directly in our model. Just for being quick, I just have the same model with all the different trains and different speeds already analyzed, so I have the results ready, so you don't have to wait the time that takes the model to run all these different cases. So what you can do is just go, for instance, if you want to check accelerations for a specific load case, you can go to deformations, deformed shape. And when you're checking the results here, you will notice that you have all the different time history analysis similar to when you're running envelopes. You have maximum values, minimum values on all the values for this time history load case, the A1 at 180 kilometers per hour. So, for instance, if you want to check the peak acceleration values for the load model A1 at 300 kilometers per hour, I need to check this load case, absolute acceleration. I'm interested in all directions, fine. I'm just gonna click on values and I click OK. So this is the envelope of accelerations. And for this specific load case, for this speed and this train, the peak acceleration value is not at midspan, as you may think that's the obvious case, but in this case is at this node, that's 1/3 of the length. So that's node number 21. Another thing that you can do to extract results is, instead of getting the envelopes for a specific load case, you can use a time history graph. So it's going to give you for a specific node, I've selected the node 21, specific output, in this case is acceleration in Z direction, and for a specific load case, in this case is the train A1 at 300 kilometers per hour, I can just plot the results. And this is how the acceleration looks like plotted against time. So it starts at 0, obviously, and starts oscillating in a forced vibration. And somewhere here, 5 point something seconds, the train leaves the deck, and then you have free oscillation of the deck, and since you have a damping value, this fades away. It's very important that you check this kind of graphs because you want to make sure that you have run the model long enough to capture all the time that the train is on top of your bridge. It's when you will have the peak values. If you just run this model for 2 seconds, maybe you're missing one peak value here at 4 point something seconds when the train is still on top of your bridge. Right, you can plot that as frequencies as well. And that will help you to understand which frequencies are more excited and if that makes sense to you. Usually, lowest frequencies means you need less energy to excitate the motion of your bridge. So usually are the ones that have greater contributions. If you look at that and you have everything 0 for the first frequencies, and then you have a frequency for the mode number 80 that is contributes to the whole vibration, then maybe something is wrong. Maybe it's fine, but it's worth it. You're checking that if the results make sense. Right. Another thing that you can do is extract results as a video. Also helps you to see how the train your bridge behaves. In this is not the same load, the study case. This is a multi-span bridge, but I thought that was interesting to see how the load moves along the bridge, and then you can see all the flexions. Useful as well to see if there you have any spurious results and there is something wrong. You will spot it very quickly in the video. All right, and last but not least, you need to plot big acceleration for all the different speeds. For the train model A1, I've done that, and then I see that for speeds from 140 to 300, it's not a big deal. Maybe I have a speed around here that makes more magnification of the acceleration, but I really have a resonance speed around 395 kilometers per hour over here. I have to do that for train A1, but for all the different trains as well, up to A10. And then you will notice that the resonance speed changes depending on the train. For instance, for the train A10, this is a resonance speed around 300 instead of 395. In this case, we have assumed that it is a ballasted track. So quickly you can see that the maximum acceleration is beyond the limit. Limit is 3.5 over here. So we are fine. There is no safety problems with track deterioration or derailment. You need also to check other outputs like every force and deflection that you need to check your bridge. You have to check your dynamic results and see if they are most onerous rather than your static load case. So what you can do is plot the dynamic results against speeds like this. This is the bending moment at midspan. And then in the same graph, plot the results for the static analysis multiplied. This is static analysis multiplied by the dynamic amplification factor. So in this specific case, this static load case and this factor is most onerous, so you can use that for designing your bridge. In other situations, your dynamic results might be most onerous, then you have to use them to design your bridge. Okay, so I'm already hitting my hour, so I'm going to be concluding now. So resonance and dynamic magnification. It's very important to understand that it's especially relevant for speeds over 200 kilometers per hour, so high speeds, and that short span structures are particularly prone to this problem. I've had discussions with colleagues that asking me, well, should I worry about my bridge? It's a very tiny bridge, very short span. So I don't think that can be a problem for my bridge. Well, you have to think just the opposite. If it's a tiny bridge or small bridge and it's a single span and it's simple supported, then it's really susceptible of having this problem. The resonance speed, it's difficult to anticipate the resonance speed for most structures. I'm saying that because if you have a single span structure, you can use analytical formulas, but when you have the change on stiffness along the bridge, or you have a Grillage model, orthotropic, or more complex bridge, it's very difficult to get any feeling of which is the resonance speed unless you run this dynamic analysis. And to really capture with this the resonance speed, you need to run a series of analysis at the different speeds, like 140, 150, 160, and then identify which are the areas with more resonant results, with greater amplitude, and then refine the speed step over this area to get the resonance speed. Model property is very important to check very carefully: mass and stiffness, and use upper and lower bounds. The analysis, you have to take into account that requires numerous time history cases. If you have like 10 trains for 1A to 110, and you have to run it from 140 to 480 kilometers per hour every, let's say, 10 kilometers per hour, that's a huge amount of load cases to run, like 400 different time history load cases. Every time history load case takes a while, so 400 of them takes much more. Last thing, result interpretation is very important. You carefully check your results, make sure that they make sense, and then that you're capturing these resonance speeds and the peak values, so you're designing your bridge to the most onerous effects. Okay, that was all for today. Hope you enjoyed the webinar. You can, I will try to respond some. I see that there are some questions now. We try to respond them. But if you have further questions, you can always contact MIDAS at the global support website, or this address over here. So let me check which questions we have. First question says, fundamental frequency is not within limits of the figure 14, and therefore dynamic analysis is not required. Let me check this out, but should be within limits. Maybe I haven't said that is which are the limits. Yeah, so this is where we have our 30-meter span bridge and 6.1 hertz. And it should be within these limits, this one and this one. So if that's within limits, then we should continue like this way. If it's not within limits, then we need to agree with the relevant authority. If they agree to continue with this design, or we need to change something in our design. Next question is, in MIDAS, when entering material properties, you can apply damping ratios to the materials. You can also apply model damping when considering time history loads. How are each of these applied, and should both be considered, or is one preferred? In the bridges I've been considering, they are concrete, pre-stressed concrete boxes or composite steel structures. So I'm using the values from the codes, and that's basically these values over here. So I'm using an overall damping ratio for my analysis of 0.5% if it's a composite structure, of 1% if it's a pre-stressed concrete. But depending on the kind of structure that you're working on, you may consider using different damping ratios for different materials. That actually is up to you, and depending on the kind of structure. which structural damping is better to be considered for dynamic analysis? Model damping or mass and stiffness proportional damping, Rayleigh damping? Will there a considerable difference in response based on the damping method chosen? My experience is when you are designing a bridge that you don't have any monitoring results of a structure, you will not have values that allow you to differentiate between which damping ratio can be applied to mass and which one is applied to stiffness. And the codes give you these values that is for model damping. So that's the ones generally things that should be used for a new structure. Another situation, if you are assessing a bridge that you are able to monitor, and then you can assess which are the damping ratios for mass and stiffness, then you can just use these values from the monitoring that probably are more accurate than these ones over here. Next question. Can you please explain the difference between model and direct integration? Yes, sorry I couldn't go more into deep with that, but model integration, what you do basically is extract a certain modes from your eigenvalue analysis, and then you use a superposition of these modes and to see how your loads excitate these different modes, your loads are transformed to oscillations with Fourier transforms, and then you can all the loads are just transformed to what is the contribution to every different frequency. The good thing about doing that is less time consuming than the time integration, and for linear analysis, that's a common way of using it. Time integration means that you just check the balance equations and you solve the stiffness and mass matrix at every time step. And that means that you can consider any kind of analysis, linear, non-linear, any kind of properties. So it gives you more flexibility on how you consider and your model. The problem with that is, since you have to run one analysis for every time step, and you for instance, if you are using 1 second of overall time and 1 millisecond as a time step, that's 1,000 steps. That means running 1,000 analyses, very time consuming. And the other problem is with the time step, the errors can propagate much more easily than the model superposition. So with time integration, you should go to even smaller time steps to avoid any numerical problems. But the model superposition is much more stable. In this kind of analysis, usually model superposition is used first because you're gonna you want to choose which modes to use in your analysis. Second, because it's much more stable, and the third thing is because it's less time consuming. Another question: what other finite element softwares are able to run this type of analysis other than MIDAS? Is Losers an option? I'm not familiar with Losers. Sorry about that. I know that other softwares are able to run this kind of analysis. Yes. I mean, it's really, you can check to the software provider and see if they can run model superposition model superposition time history analysis, and then if they do, then this kind of model can be done. Would it be possible to circulate the Excel spreadsheet used in the presentation? I'm not sure about it. It's not because I don't want to share it, but when you share this kind of information, then you have responsibility that the spreadsheet is robust, watertight, and doesn't have any glitch or anything else. Rather, and it's a spreadsheet that I've prepared for myself, and I'm working with when I'm working with these kind of problems. The truth is, it's not difficult to prepare one by yourself. That probably matches better your workflow. And as far as I'm concerned, MIDAS is preparing as well some additional tools to run this kind of analysis, so it will be implemented in future versions. You can also always contact them for this. You spoke about underestimating the time step. Can you speak about overestimating it? I understand that overestimating it is like saying, I'm going to be safe, so I'm going to use 0.1 milliseconds for my analysis. Well, it's not harmonics. You can use 0.1 or even less than that. The only problem is the smaller the time step, the longer will take to run the analysis, and the size of your output files is going to increase exponentially. So you have to be careful. My recommendation is for a specific structure, get your model ready, run just one train at one speed, and make sure that you're getting nice results. Do a sensitivity study, try to reduce, try to increment the time step, see if that has a relevant effect. When you're happy with it, then run the other route cases. What's your opinion on the slab track versus ballast track debate for HS2? I'm not sure if I'm in a position to respond that. Obviously, there is an implication for this kind of analysis. And this problem. But as far as you are using the codes and you're making sure that your accelerations are below these limits for ballasted tracks and for ballastless tracks, you should be fine. So I understand that the debate is somewhere else. Okay. That's all for today. Hope that you have enjoyed the webinar. As I said, if you have further questions, sorry, I cannot respond any more questions. You can always contact me, or you can contact MIDAS at the global support website shown on screen, or you can contact via email at uksupport@midasuser.com. Thank you for joining. Thank you.